Good afternoon, everyone. We're ready to start our seminar. So huge welcome to everyone who are here with us today for another exciting talk on the Dalton seminar. Today we have Jeannie Thomas, who works at the UK Atomic Energy Authority on the Spherical Tokamak for energy production, also known as STEP program, which has the mission to deliver a UK prototype fusion energy plant targeting 2040. And a path to commercial reliability of fusion. He is a part of the commercial pathway team and looks to establish the steps needed between the prototype and the future commercial plants and identify market factors relevant to successful commercial plant capabilities. So he started his degree in physics at the University of Southampton, and now he works in the nuclear energy sector as radiological protection specialist in decommissioning before moving on to manage expert working groups on these topics for the World Nuclear Association. And prior to joining at the University of Bristol, where he helped to establish the Southwest Nuclear Hub. In this talk today, you will hear about the potential role of the fusion energy plant will play in the future net zero economy, and about the pathway that lies before us to get us there. We will draw on the work done in support of the STEP program and give an insight into working at the UKAEA and its ambitious development program to put this prototype plant on the grid. So the talk will follow with a Q&A session, and we have for people who are joining us online, we'll ask you to put your questions in the chat. And then for people who are here, you're more than welcome to have a question session. So, Jamie, thank you very much for joining us, and the floor is yours.
Thank you very much for that introduction. Very good. And yeah, thank you for inviting me to be here. It's very, it's a big honour to come and speak at the University of Manchester, and I'm more used to kind of organising seminars than delivering them, so you have to cut me a little bit of slack. I'm going to talk a bit about the UKAEA STEP programme today. What I'm not going to talk about is a lot of detail about fusion, the nuclear physics of fusion. There's loads of really good information out there on that. I'm going to touch on it because it's obviously relevant. I'm also not going to go like into loads and loads of detail about the fusion technology. Like you're not going to hear, you see lots of engineering drawings of what a superconducting magnet looks like and all that kind of stuff. So I'm going to talk about fusion energy, its role, and how we're going to go about realizing that potential for fusion energy. One of my aims here is also to try and build more bridges between the academic community, so people in research, and our program at UKAEA. STEP is breaking new ground in all sorts of areas where fusion, as a fusion lab, which the UKAEA hasn't looked at before. So there's going to be a massive need to get loads of new thinking, new ideas, new experts involved in fusion. So if I can play that role of helping to connect people to the fusion program, then absolutely I will. So I will talk for maybe half an hour, and then there should be plenty of time for Q&A afterwards. So ask me about that, and if I can answer the question myself, I will do. I'll definitely also connect you to some of the world-leading experts we have back at Cullen who are working on this. So what topics I will cover, then I said what I'm not going to talk about. So I'll talk about the fusion in the UK and its kind of global context. So for those of you who don't need to know anything about fusion, I'll cover a little bit about what it is and where it is. I'll talk about the STEP programme, because this is the UK's mission to put a power station on the grid in the 2040s, and this is a really ambitious program by the UKAEA, so I'll spend a bit of time describing just what that's trying to achieve. And I'll talk a little bit at the very end about some of the work that I've been personally involved in, and that has largely been looking at strategic materials, the materials we're going to build the fusion reactor out of and where we're going to get those materials from. And so enriched lithium is one of the ones I've been looking at most closely, so I'll talk a little bit about why we need that and what we're doing about trying to get some of it. I thought I'd start off with a very brief introduction about myself. Having come to many university seminars, either as a student or when I was working at the University of Bristol, I feel like it's always interesting to hear about people's career paths. For people who are working in research, if you're a student thinking about your next steps, or if you're working in research and thinking about taking those skills out into industry in the future, I think as someone who comes from a physics background, I thought I'd just explain about my career path as being like, in the hope that it might, help people think more broadly about the sheer variety of opportunities that science, engineering, and STEM subjects can get you into. So I started my career having finished a physics degree that was nothing to do with nuclear, working in the nuclear decommissioning authority, in the Magnox program. So taking apart these first generation of nuclear power stations that were amongst the first in the world, that adopted all over the UK. These are graphite moderated CO2 cooled reactors. They're very big. They're very old technology, and they were running for many, many decades. But many of them, all of the Magnox ones now have reached the end of their life. And I was involved in decommissioning those reactors. So that was a radiological protection role, involving keeping people safe from radiation while they're going in, decommissioning either the parts of the power station or some of the ancillary buildings around it, like fuel cooling bombs and so on. So that's a picture of Dalton, which is just entering into its care and maintenance period, which is the classic 3-box model, as the NDA calls it, which is what is left behind when they've effectively finished doing most of the decommissioning of the power station. You've got the 2 reactors that it's immediately waste will remain behind, just sort of undergoing radioactive decay until the hazards in those buildings have gone down in the reactor, and then turn those to brownfield sites. Usually after a few decades of waste to cool down. Then I worked for the World Nuclear Association, so I kind of took my radiological expertise or experience from industry and worked for a global trade association. And that was really interesting. So I was managing expert working groups there, looking at radiological protection, particularly international standards, and how organizations like the UN and other scientific bodies set standards in that field. And it really exposed me to the global nature of the nuclear industry. So the way in which think of nuclear power stations as being very much like domestic products of national governmental programs, but actually the industry is completely globalized. People trade in the technology and materials all around the world, from how uranium comes out of the mine in an ore and ends up as a high-level waste and via a reactor in between, and high-value fuel products in between. So that was a really interesting part of my career. Most latterly, before joining UKAEA, I was at Bristol. So they have sort of large research program in science and engineering at Bristol. It's one of the top engineering universities in the country, and they do a lot of research that relates to the nuclear industry. They don't have a research centre as such. So when I went to Bristol, it was all about trying to link up their research with industry more. And in the end, we created a centre that does a kind of a smaller version of what the Dalton Institute here does. It brings people from different disciplines together, working on challenges that overlap. It helps industry to engage more strategically with academia, kind of like the Southwest UK. And then lastly, I now work at Cullen. So that's a picture of the jet reactor at Cullen, which is the joint European. But that's how I kind of ended up back into the fusion and talk about what on earth it is I'm doing then. So I'll just start off a little bit talking about what fusion energy is then, because I feel like it would be brave to continue down the talk without at least describing what it is in very high level terms. But I'm not a plasma physicist, and so you'll have to go somewhere else to find the real detail of this. Only one equation in the entire presentation, and that's not the very end. And even that's very, very, very simple. So that's the kind of level of talk you're going to get today. So basically, fusion is about fusing light elements together as a corollary to nuclear fission, which is about splitting heavy atoms. So it's both a nuclear process, and due to a quirk in the way that the nuclear stability works, you can release energy both by splitting heavy atoms and, from the other direction, by fusing the very lightest elements to create stable nuclei that release energy. So we take the really very lightest elements, isotopes typically of hydrogen, sometimes of helium, and fuse them together. It's the same process that goes on in the sun. So in the sun, the immense gravitational pressure drives the confinement that keeps the atoms together, makes them hot enough, and then eventually allows them to overcome their natural repulsion to eventually fuse and create energy. We aspire to recreating that process on Earth, and that's what the fusion reactors around the world are trying to do. We want to do it in a slightly different way, in as much as we don't benefit from either the size or the gravitational mass of the sun. So if we want to produce meaningful amounts of energy, we've got to do it without gravitational confinement and without the immense size that the sun has. We need to do it in a much smaller space. And so that actually means we need much, much higher temperatures, even than in the center of the sun, talking about order of magnitude higher than in the center of the sun, in order to recreate those processes here on Earth. So we're talking about 150 million degrees as a kind of order of magnitude. We've got to heat those atoms up to get those fuse. So that's what fusion energy is. When we do so, we release energy. Oops. And the long-term aspiration since fusion energy has been dreamt of has been to harness that energy as an energy source. And if we were able to do that, then it would have a number of benefits. And you'll recognize that a lot of these benefits are quite similar to the benefits that you get from conventional nuclear. So it's low carbon and it doesn't use up much space, much like a conventional nuclear reactor. It's reliable in the sense of it's a dispatchable energy source. So you don't have to worry about the environmental conditions, the wind or the sun. You can turn the reactor on when you need the energy. So it's dispatchable in that sense. Sustainable in the sense of its fuel sources. If we think of its fuel as being primarily deuterium and lithium, then it's got many of the similar advantages of nuclear, as much as, because it's a nuclear process, you get a lot of energy per kilo of material that you use. So in terms of making the most of the Earth's resources, it's very sustainable. It's very efficient because it can operate at high temperatures. It operates at a small footprint. It's very, very dense. It's quite efficient process. Its probably main difference from conventional nuclear is it does have a different approach to safety. It doesn't have a core with all the fuel assembled in the core and then a chain reaction that's controlled through the use of rods and moderators and so on. It's actually the fusion reaction is created by a high temperature plasma, which has to be very finely controlled in order to create a fusion reaction. And when those conditions disappear, such as magnetic fields and so on, then the reaction stops. And so it's kind of a very unstable process in a good way, in so much as you don't need to do very much to show. It has different hazards from nuclear fission, and it doesn't have that decay heat / chain reaction challenge that nuclear have to cater for. This could be an entire talk on its own. In fact, it could be an entire conference on its own, in terms of the energy system that fusion is going to find itself in is uncharted, unmapped, and unknown. We're talking about the second half of the century when we're going to have significant, input to the energy system from fusion at the earliest. So, that forecasting what the energy system is going to look like in that time is actually quite challenging. Even the big energy agencies like the IEA and the IPCC and so on, when they look at scenarios, tends to go up to about 2050. They go much beyond that in terms of trying to forecast what our energy system is going to look like. I think we can say a couple of reliable things, though. We can say that the global energy consumption is almost certainly going to be higher than it is today. It's going to grow. The population of the world is probably going to grow, but even if it doesn't, the number of people that have access to energy and the kind of quality of life that requires that much energy is still quite low to this day. So as we bring people out of poverty and as we develop, the rest of the world into the advanced economy that they aspire to have, they'll be using. And we want that because that improves people's lives, it improves people's health, and all of these things are driven by energy consumption. So energy is probably going to grow. The other thing, which I think we can probably reliably say, is it will be different. So we have an energy system largely based on fossil fuels at the moment. They're kind of very advantageous because they're energy dense, easy to move around. But in the future, we're going to have to rely on different energy sources. And particularly the energy vectors that move that energy around in the system are going to be different. So there's going to be almost definitely an increasing role for electricity. We see electrification as a means of moving energy around is getting more even today, and it will probably continue in the future. And there will be other new vectors which currently are either not around or very small. Particularly, people talk about hydrogen as being a fairly dominant way of moving energy in the future, either with transport or for heating homes, so on. So the energy system is going to be different, and I guess what I'm saying here is that fusion will land in a system which will need to find its way of producing the most valuable product, thing that we as a society need the most, and which fusion is most ready to, uniquely, ready to deliver. And so these are some of the energy products that we can think of from a fusion reactor. And one of the good things about fusion's longer timescales is it does give you the opportunity to think, to rethink the energy system a little bit more, and think from first principles, what is it we really need? And at its most basic, fusion plant will be a source of heat and source of nutrients. And we can use those two energy outputs, if you like, in different ways. So for heat, we can obviously produce electricity. That's what most power stations do today. We can heat into steam via turbines. But we can also use heat more directly. We can use it in increasing the efficiency of hydrogen production and making synthetic fuels. We can use it for heat as a product in its own right, district heating for city heat, driving desalination, say high-grade heat going back to. But we can also use the neutrons, and that's another potential avenue that fusion can go down. We can use that for making isotopes, either for medical purposes or for industrial purposes. We can use it for making more lithium. That's a fairly self-serving ambit. But we can also use it for silicon engineering, for supporting both scientific and industrial research. So there are lots of different ways to use fusion energy. And in our sort of commercial pathway group, we tend to sort of think about this in, you can cut this cake a number of different ways, but where that it's cut here is that you can think of clean cities, clean industry. So it could be things that help people who live in the cities, and it can be that can help drive the industries. So what I'm saying here is, I guess, not drawing any particular conclusions, but I'm saying that there is a wide range of different applications you can use fusion plant for, not to think of it just as an electricity producing machine. And if you want to know more, most of this is taken from the little leaflet I've got here, which is something our group produced, which is Commercial Fusion Energy, Electricity and Beyond. And it kind of goes into a bit more of some of the detail behind some of those. So I'll leave those behind. Absolutely feel free. Right, skipping back a little bit, I think it was also probably foolish to have a fusion talk that doesn't at any point particularly fusion. I should say that the type of fusion that I'm talking about here is just a subset of the types of fusion plant which are being pursued around the world. Broadly, fusion kind of drops into two big categories of magnetic confinement and inertial confinement. And there are kind of combinations of the two. But what I'm talking about here is magnetic confinement, which is where we use magnetic fields to confine the charged particles, keep that plasma hot and away from any structures that would either damage or so that if what we've got here is some of the historic and future reactors that have been developed and operated. So the UK is I think it's fair to say, a world leader in fusions. And I think most of that comes from its heritage of operating the JET reactor, Joint European Torus, which is at Cullen, where I work. It's coming to the end of its life. It was, and I think still is, the largest tokamak operating at the moment. It will be replaced by ITER, which is the moody-looking black and white one here, which doesn't give a sense of scale because this one is vastly bigger than JET. JET is designed to just sort of prove some of the concepts behind fusion to run longer duration power pulses, but it's limited because it uses copper magnets, and it's kind of reached, if you like, the end of where it can demonstrate new scientific breakthroughs. So the next step is to go to ITER. So this is a vastly bigger machine. It still has magnets, but instead of these copper magnets, it's got low temperature magnets. It will also use energy gain, which is something which you hear about a lot if you read about fusion and what we're trying to achieve. The idea of an ITER is that it will, whereas JET consumes more energy than you got out of it, ITER will produce 10 times the energy in the thermal energy in the plasma that we inject through the heat to get it going. So that's the aim really for ITER, to demonstrate that energy gain. But what it won't do is do anything useful with that energy. It won't generate electricity. It will just prove that you can get more out of it. And then it would be to next generation power station demo, which is coming further behind ITER, which will demonstrate things like fuel sustainability, that actually running the power plant in a longer than just a few minutes of pulse at a time, and also putting some power onto it. The UK has also run a reactor called MAST, which is the mega amp spherical tokamak. Whenever you see SP in fusion context, it usually means spherical tokamak. And that means that instead of jets, slightly squashed donut shape of plasma, it has a much more compact kind of chord apple, is the best way I've heard it described, shape. So it's much denser, and could be could offer a slightly more advantageous route to a commercial reactor than these very, very large machines. So you can see the size, you can't see the size of I could demo jets to ITER or orders of magnitude increase in size complexity. Spherical tokamaks could offer a more compact option. It has some advantages, it has some challenges. One of the main challenges being with compactness comes a challenge in terms of getting the heat out. And so really the main innovation that the UK has come up with is the diverter leg at the bottom, allow us to spread the heat out and therefore into the realms of the materials that actually may be able to pick this and divert that heat and make it useful. And that is the technology basis that STEP is going on. So that's spherical tokamak. I'll skip over that one because that's. I'll talk about STEP. Before I talk about the STEP technology, I thought it might just be interesting for people to sort of have a little bit of an insight of what it's like to actually work in a program like STEP, where we're trying to achieve something incredibly ambitious with lots of unknown technology solutions, which we're able to discover along the way, getting there, and therefore living with almost permanent uncertainty and ever-present change, when we need to adapt the program to take a different direction. We thought we were going one way, and then we decided another way might be better. So a very kind of large, complex, interrelated challenge where there's lots of competing priorities. Almost any time you make someone's part of a plant perform better, almost guaranteed to make someone else's part of the plant perform worse. And so that's just the nature of these integrated machines. And so that competition between, if you like, different people trying to advocate for their own priorities could create this really toxic, really poisonous environment where everyone's sort of fighting for their own patch. it's really hard to make any progress. And I think the fact that the UKAEA has, at least from my experience, avoided that and has a very good working relationship, I think is because of the people that work in it and because of some of the values which I think are captured by their program and charter. So you see these kind of values along the bottom, which I found quite, eye-opening when I joined the program. The things like kind and compassionate, I think, is a really important value which UKAEA takes seriously. And is evidenced by the way people support each other, share their knowledge. People are incredibly generous in sharing their knowledge. I don't think a program like this would be able to agile and pragmatic, I mentioned that. Taking bold decisions, but being prepared to change them as well as things like ambitious, tenacious, and pioneering. That feels like it's at the heart of the program. You can't be inclusive, transparent, and kind to people. So I thought that was interesting to see, STEP is reviewing this charter and it always needs to do with the program phases, but I think that's an important part of why the program is the way it is. I suppose it's worth reflecting the kind of context in which we operate. The UKAEA is the UK's Fusion Lab, or National Fusion Lab. It has its own mission. STEP has a much more focused mission within that, if you like, and I'll talk about those in a minute. And then we also sit within the context of a wider government strategy on nuclear fusion, which is around how do we create that whole set. So in terms of
Can you just press the line?
this one, minimize it like that. Okay, cool. Let's make sure that's still moving. No, that's fine. Cool. Right, so mission. So what is it we're trying to do? The UKAEA has its mission, so to lead the delivery of sustainable fusion energy and maximise the scientific and economic benefit. And then kind of within that, STEP has a much more focused mission. So to deliver a UK prototype. So this is a specific machine in a specific place. It's going to do a specific thing. How we will judge whether that's been successful or not. In a specific time frame, so targets in 2040, and to create kind of commercial viability of fusion along the way. So to create some of the essential aspects of a commercially viable fusion sector in the UK along the way. So that's what we're trying to do. And this is what the actual prototype is trying to achieve. It's kind of some of the key success measures, I think, that we will ultimately look back and say, how well does our prototype work? What have we managed to achieve by building? Clearly, one of them is going to be to put net power onto the grid, and I think that is a really important thing with fusion to say that it's done. And if it does that, then that would be a world's first. It will need to accelerate deployment. So it won't be good enough if we go down designing a particular machine that can't ever, it's kind of a bit of a technological dead end, and we go any further. It needs to bring fusion forward and make it faster. It needs to demonstrate that there's potentially competitive life cycle cost for fusion, because I think if there is probably the biggest challenge that fusion faces is convincing people that not just that we can do it, but that we can do it at a cost that's sensible, not just for building and operating the plant, but also for fuel and for the decommissioning price at the end of the life. It needs to demonstrate the fuel sustainability. That's really important because at the moment fusion reactors consume tritium, and tritium isn't a natural resource. So we need to find ways of closing that fuel. Otherwise, we'll only ever be able to operate reactors for very brief periods. High plant availability. Again, that's closely linked to its potential to be a commercial energy source. You need to be able to have your reactor available if you need it. Safe and environmentally compliant. Obviously, that runs through absolutely everything. Every part of the fusion industry is like, and it feels like it needs to be sustainable, safe, and development flexibility, which maybe that doesn't quite obvious what that means. But once we've built the prototype, it needs to it needs to be exploited for the maximum benefit that we can. So we will be able to learn from operating it, and we will be able to see materials that have been irradiated with relevant neutron spectra fusion that needs to become both a power plant and a kind of a test bed in itself. At the moment, we are just coming to the end of our first tranche of funding, which was about 220 million to get us to the end of 2024. And that's kind of where the program is at the moment. We have a site where the prototype will be built. So we went through a site selection process over the past few years. This was before I joined, but was announced relatively recently that we'll be planning to build the prototype at West Burton, which is it's quite a big site actually. Here's a sense of scale. It's in the nearest town, and their site it might visit the entire whole town. But 2,500 megawatt whole units, which are now closed. With much smaller gas up here, which is going to remain. The rest of the entire site, including where the old pulse power station will eventually be decommissioned, is the site for STEP. So that's kind of at the junction between Nottinghamshire, Yorkshire, and Lincolnshire, I think. There, it's a relatively rural area, so we've got a whole load of new stakeholders to engage with there, but that's where they're planning to build it, so the Trent. And there are real people working there. So these guys are UKAEA people at the site, doing things like getting ready to fully characterize the site, because we need to understand everything we can about it. And it is a particularly, the characterization would be a particular challenge, given that it's a whole type application, so you think of lots of coal ash that's been left behind at the end. So we'll need to understand what we either do with that or reuse it. And again, another talk that could take an entire session is the kind of disrupt fusion at the moment. In the last 2 years, there's been huge increase in the amount of private money, commercial money going into reactor developers, if you like, developing different fusion concepts, particularly in the US. Commonwealth Fusion Systems is one of the biggest. It's received funding recently from the DOE as well as the private sector. So there are now a whole bunch of private companies who have their own various approaches. Some of them quite different. So like First Light is inertial confinement, so looking at colliding targets together to create the shock waves that induce fusion in a pulsed way. So very, very different approaches. And we're in this kind of like, feels like a very exciting time when lots of people are doing different approaches and we don't know which ones are going to have what advantages. So there's now been, like I said, in the last few years, over 5 billion has gone into this sector, and that's actually quite substantially more private money than public. So all over the world, North America, Europe, Asia, Australia, developers all over the place. And so finally, I'll just talk a little bit about some of the work that I've been doing in the STEP program. So like I said, I work in a team called Commercial Pathway. We are a relatively small team within STEP that looks at it sounds like the journey beyond the prototype and how commercial reactors may look and whether they are different or not from the prototype that we're developing, and where those differences lie, and understanding how the differences between our prototype and a future commercial reactor are, and what we can do to make ours more commercially relevant, and to understand the differences where they have to remain, and to look at some of the activities that are not strictly about developing a reactor, a prototype, but are essential for the whole fusion sector. So hence enriched lithium. So enriched lithium supply chain has kind of touches on really two parts of the STEP mission. So one of it is about the targeting 2040. So it means that if we want to operate our reactor with a tritium breeding system to it, integral to it in 2040, then we need the breeding material on it. So we need to have a enriched lithium supply by 2040. at the latest. And it's also really linked to this commercial viability, which is to say that the rest of the fusion sector will also need a supply of lithium. Most likely, a large part of it will need to be enriched lithium. And I'll talk about what that means in a minute, say enrichment. And the UKAEA has defined kind of six challenges of fusion, and lithium is really kind of at the heart of one of those fuel handling, it says here, but yeah, it's all about fuel sustainability. How do we breed the tritium we need for fueling the fusion reactor that we want to create energy from? So here is your one and only equation. I did say it maybe it's going to be simple, and that's just to illustrate that lithium is relevant to fusion really only because it's a pathway to tritium. So tritium is an isotope of hydrogen. It's slightly heavier than, so you've got hydrogen, you add a neutron, you get deuterium, and then you add another one, you've got hydrogen with a mass of 3, so tritium. It's unstable, it's radioactive, so it doesn't exist really in nature. We can't go and mine it from the ground or distill it from seawater like we can with deuterium, the other fuel. So if we want to be able to drive a fusion reactor, we can't really do it in the same way that we would a conventional reactor, where we build up an entire fuel tank and then just burn our way through that fuel, and then top up the reactor again at the end. There just simply isn't enough tritium to do that. And what we need to do is breed the tritium as we're generating the power, and we do that by using lithium. So lithium is a very, very light element. It takes a neutron and creates it to tritium and helium. And I've listed here lithium 6, which is the kind of dominant one, which the minor isotope of lithium is lithium 7 as well, which also produces lithium. In fact, the advantage of having this slightly heavier lithium is that when that gets hit by a neutron, it gives its neutron back again, and that neutron can carry on. It does absorb energy from the process, so this one releases energy. So this one tends to be the one which is the most important one for tritium breeding. And it's common to anyone who wants to use tritium as fuel. So anyone who's using the deuterium tritium fuel cycle, which is the majority of fusion development, and using that particular fuel cycle, in particular 2 variants of hydrogen fuel, then they'll all need tritium, they'll all need lithium, and we'll need to get their lithium, get the tritium. So it's kind of a common, you can think of it as a fuel, proxy for fuel is the reactor. You can think of enrichment boosting that lithium 6 component as a kind of fuel cycle service. So no step prototype plant will need it. We don't know exactly how much. It will be in the order of something close to 100 tons, something roughly like that. And it will be sometime by the time we need the reactor. Again, we don't know exactly, haven't pinned down that exact scale yet, as to when we need to go to tritium breeding operations on the plant. It may be slightly later, but more or less we can assume that we need it sometime before the plant starts operating. And then you can play games with numbers to try and forecast what on earth the fusion sector might look like in the future. And it's very difficult to do, but if you can imagine a global fleet of reactors that are both operating and under construction, then we can imagine that once the fusion sector agrees to reach maturity, it could be several thousand tons a year of this particularly high value, high energy density material that could be big for. So this is kind of a global market, say, in lithium, enriched lithium. And this is almost my final slide, and it's just to say, it's re-emphasize that point. If we do manage to find a solution to manufacturing enriched lithium in the form that fusion reactors need it, and there is a variety of ways in which they could potentially need it, depending on exactly how they're farmed. But more or less, the enrichment step could be common. There could be a global market for that. In the UK, as is being forced to solve this problem for STEP, could then have kind of a leading position in supplying that material and expertise to the rest of the world's fusion reactors. There's definitely time and space to develop the new technology that we need. So we don't need the enriched lithium tomorrow. There's time to develop really commercially competitive technologies. And I guess one other thing to say is that working with lithium is not some kind of secret technology that has been unique to fusion. Like lithium as a material is really highly sought after for the energy transition more generally. They're not interested in isotopic enrichment, but they're interested in high purity lithium. And so there's an opportunity for us to both collaborate with and to seek technology transfer from outside of the fusion disciplines. There are a couple of challenges when it comes to enriched lithium, which I just mentioned, and won't go into, but they mostly relate to the way that we need to regulate its use. Firstly, technologies we've used to enrich lithium in the past, that has been undertaken in the past, and have tended to be environmentally and safety have high risks associated with them. They tend to be very mercury intensive processes and hard material to work with. So we need to find something which is licensable as a test and contaminate the environment. We want something, we don't want a fusion fuel cycle, this lithium fuel cycle, to become the Achilles heel of fusion. And secondly, it's a dual use material, so it's got applications in the defense sector, where it's used in nuclear weapons. So as highly enriched lithium-6, we need to make sure that we create this new market without increasing the global security risk. And there are ways to do that, which would enable it to be fortunate or nice regulation that enables us to realise that dream. I think that's, yeah, more or less the last one. That's just a sort of a flag, which I imagine those who are interested in the room probably already know about it, but there is a no longer upcoming but now live challenge, industry challenge. We're looking for ideas and technologies that could support lithium's role in the fusion fuels. So enrichment is obviously an obvious one. So is things like how do we extract the tritium from the lithium? How do we measure the lithium, the tritium dissolved in the lithium? How do we manufacture the lithium into forms that the plant needs from the form that it might have? So that's open now. I think that is my last slide. So yeah, as I promised, hopefully we've got some time for questions.
Thank you so much, Jamie, for such an insightful talk. Do we have any questions from the activity?
Actually, the concept design, finalized
So I think the concept, if you're familiar with the there's an analogy taken over from NASA's TRL to concept maturity level, CMM. So if you're familiar with that way of that terminology, then it's CMR5 is what they're looking for to get to. I'm not an expert in that, so I don't know really much what that means. But what it means is it's enough that we can start to fix certain aspects of the plant's design that we can now actually start to. Because as I kind of mentioned before, every time you change one part of the plant, you need to change all the other parts as well. Every time you make more space for this, you suddenly get less space for that. And so I think the concept design has to be to a point where we can now start to think, okay, we've iterated it to a point where we can now start looking at things like not just how the plant's going to be configured, but how we're going to maintain it. That kind of thing. So start to fix some of those parameters. Yeah, that is a very interesting question. One thing that lithium has going for, I suppose one thing I would say is that I think it's actually good there is a demand for lithium, if you like. It might sound counterintuitive. It means we need to compete really hard to get hold of the material. It's obviously going to be a scarce and strategic resource. But it's actually slightly better to have that situation and to have nobody else interested in it at all. You have to create an entire industry just for this one material that nobody else wants to buy from. So in some ways, it's not a bad thing that we've got other competitors out there that want to manufacture things with high purity lithium. The other good thing is that the other industries that we essentially competing with for that lithium don't care about its isotopic enrichment. So we can spend a lot of time and energy enriching it into this specific product for fusion, and we'll create, if you like, tails of isotopically depleted, if you like, and kind of lithium-7, which will be perfectly usable for sectors. And then finally, I would say that, yeah, I will come back to that like analogy that it's a nuclear process. So we get a lot of energy for every kilo of lithium that we use, that we successfully turn into tritium and then use into energy. I think Ian Chapman, who's the director from UKAEA, overall, I think if I quote him correctly, his good stat is something like the amount of lithium you get in a typical laptop battery is enough. It's enough for one person's lifetime energy requirement. So you can see there's a bit of an order of magnitude difference between the amount of lithium we need potentially for fusion, that will become significant as more plants come online. But it's probably never going to reach the order of magnitude if you were trying to electrify the entire transport fleet. Now that's another question, which I don't know the answer to. Is there enough lithium for all the transport fleet in the world? I'm worried about that.
Isotope separation and that is fairly intensive. And the moment tend to do it in fairly delicate emission quickly. So if you've got to get the deuterium and the lithium, how do you get the carbon from the DP? You do that, you don't move back from your electricity.
I see what you're saying. You mean, do we end up using more energy?
Well, not more, but you're using quite a lot, which goes into your energy efficiency.
Yeah.
That sounds like quite an energy. I don't know.
Yeah, it can be, and that's why we need to find technologies that are not just good at giving us the enriched lithium product that we want to the highest specification that we need it, but also do it, like you say, without using too many resources and that kind of thing. So we need to find the right technology to do that. But if we do, then again, the amount of energy that we'll get back from fully utilizing enriched lithium will be very, very high. So I think we can certainly see pathways to where we're getting lots more energy back than put into enrichment.
I mean, like the
Yes, well, particularly, yeah. So lithium-6 is the material and the technology to enrich
that. Sounds to me like it's one more benefit for you across the list. You don't cross off for activation, and then you cross off deliberation with wasn't going to produce radioactive waste. It wasn't going to have these around.
Well, I think I would put the argument. No, there is, and I think that
those things are still positive features.
Yeah.
The time will be a little bit quiet and rough.
Yeah. I think I would paraphrase some of the private sector fusion companies and the way they see this is one to say, because the technical answer I might talk about is just what is that risk with lithium? What use does it have in the defense sector? And it's a very specific risk that requires you to already have a hugely well-developed nuclear weapons program before you could even start to use it. It's a little bit like tritium in that regard as well. You need to already have a weapon before you can do anything useful with your lithium-6. It's such a long way from, say, having a big pile of radioactive material that you could really do a lot of damage with if you just if you just had that in your possession. Lithium, very much of a kind of like twice or three times removed proliferation risk. So that's a kind of technical answer, but I think that kind of a more powerful one that the private sector ones have kind of got a good answer to, I think, is that if fusion comes along and displaces all of the world's fission reactors, then actually there's a whole lot less fissile material around. There's a whole lot that whole part of the fuel cycle, which is more directly connected to weapons technology than fusion is, will be, so they would say that the fusion's adoption will reduce proliferation risk globally overall if it gets taken up. Lithium really isn't a particular hazard. Having lots of people with the technology to enrich fissile material is more hazardous.
We have a question from the chat. So what method are you proposing for lithium-6 separation? The Folex press uses mercury, which has environmental concerns. This is from Julian Matthews.
Yes, that is a good question on what technology are we going to use. The answer is that we haven't identified that yet. So the purpose of that lithium challenge, which I flashed up there, is to come up with some of those technology ideas. So it's correct in so much as, the mercury process is behind what it's been used in the past. And that does have potential environmental and safety risks with it. I don't think that necessarily closes it off as a research route and as a potential route. Mercury may still be the solution in the future if we can find a solution that keeps the environment and people safe and hazard and doesn't produce waste that we can deal with. But I don't think it's probably the obvious, most advantageous one, but it may still work. And the answer is that there are lots of other ways of doing it. We just need to find out which is the one that works best. So, for example, there are solvent extraction processes, and people are looking at here at Manchester. There's laser-based processes. There's people who use plasmas and special ways of exploiting inertial properties of the material and separating it that way. There are lots of different pathways, and then that's why I kind of in a way say it's not actually the hardest challenge that fusion has to solve, actually the enrichment bit. It's chemical engineering, process engineering. We can probably find a way through it. But at the moment we have lots of options on the table, and we need to sort of narrow down which of those promising.
Thank you.
Right, so each of I know these in my really like is STEP going to be like moving on
Yeah, so ITER can do that because it's not actually looking to breed tritium necessarily the way it's just looking. So those test blanket modules are designed to prove or to explore different ways in which you might breed tritium. Like, are you breeding solid with ceramic pebbles? Are you using liquid lithium metal? Are you using a liquid lithium lead mixture? These kind of ways of doing it. So those modules will only breed small amounts of tritium that won't be enough to fuel the plant. It will be a net consumer of tritium. STEP is designed to be a prototype power plant, so it can't afford to, at least we believe that it can't afford to just simply be a net consumer of tritium. I think it needs realistically to be viable to breed its own tritium. So we need to come up with a solution that produces a tritium breeding ratio, of at least at the plant level, at least one, but at the system level, it needs to produce more tritium than it consumes. So yeah, otherwise the plant would need to come offline once again. We think that from commercially viable levels of power, that's quite a lot of consumed. We probably can't afford that we have to sustain. So yeah, it will need an integrated solution that can solve the problem of fuel sustainability. It won't be able to have multiple solutions. Yeah. Yeah. Yeah, it's a good question. So lithium, you can read all about this in the news, almost daily. Like lithium is a kind of key material for the energy transition generally. So we're seeing that play out. Like most minerals in the earth crust, it's not kind of uniformly distributed everywhere. It is concentrated in certain places. South America and Australia are two places that have large amounts of deposits in the ground. South America particularly there's a kind of lithium triangle in South America that has a huge amount of lithium in brines, so basically kind of like sort of waters in the high deserts and things. And Australia has produced a lot in the past. The other interesting part of lithium is not just where the lithium comes from, but where the capability to process it and turn it into a useful product is. And at the moment, that's almost entirely in China. So most lithium supply chains flow through China, even if the material comes from elsewhere. So I think, regardless of what is with fusion, if we all want to be driving electric cars, that's supply chains we need to diversify. But the interesting thing is there is lithium in the UK, so we have reasonable lithium deposits. In terms of compared to the rest of Europe, we have quite substantial lithium deposits, particularly in the southwest, around Cornwall. There used to be lots of metal mining in Cornwall in the past, and it turns out there's lithium in the ground there. So there could be a day where you could imagine a sustainable domestic supply of lithium that meets the needs of the UK fusion sector within the UK. Yeah, it's not the most geologically constrained material in the world. It's actually in some ways a more of a industrially constrained.
I have one question. Sorry. So we've mentioned lots about lithium. Obviously, any tritium that's being used at the moment for fusion applications to make big kind of reactors in Canada. Is there any reason why we can't work holistically with the fusion industry while we're building up that capabilities and building up new technology to build more country type reactors? So generate low carbon electricity, but also generating the tritium that's needed for first generation fusion.
Yeah, that is a really good question. So
So basically, most of the tritium at the moment, we haven't done the technology yet to reach the scale required for the first generation of fusion reactors. That's we're dealing with final prices for being on more low carbon forms of energy, because we build up our 100 type reactor capability, generate low carbon energy, but also provide the generation given to then feed into the first generation fusion plant.
Yeah, it's a really good question, because the biggest headache, as I see it, in terms of the biggest strategic risk facing fusion, all of those projects that are going on and growing, is that will there be enough tritium to fuel those first generation reactors? And will they all kind of start to come online at the same time and have the same demand? That is a real, I think, strategic risk for the whole fusion sector that it's very well aware of. As you're saying, the main source of tritium is this, so the CANDU, which is a type of heavy water fission reactor, which the Canadians developed, uses natural uranium and therefore uses heavy water as a moderator, and it produces tritium as a byproduct, as a kind of waste product in the heavy water. So they capture that and extract it, and that's where almost all the world's kind of tritium is used for any purpose, comes mostly from the Canadian nuclear laboratories that do that process. And yeah, I think that if we really think that we're going to need this much tritium, and therefore it has this higher commercial value, but I think that really we should be looking at options to try and find alternative way to get more tritium. I haven't seen that discussion emerge yet, other than amongst the fusion community who says, I just wish there were more CANDU reactors. And it's true, yeah, building a whole load more heavy water reactors would definitely give us a lot more tritium.
And all of this is on the deuterium tritium reaction, which obviously is there any work going on with deuterium? I know it's wanted to do, it seems like lots of challenges.
There are other programs looking at other fuels. So there's so yeah, as you say, deuterium fusion could negate the tritium. There are others that, for example, don't produce neutrons. They're aneutronic, so you don't get these kind of spare neutrons coming out, which is one of the biggest headaches for designing a power plant. How on earth do you get it to survive? Yes, the temperatures, but also the really high energy neutron flux that comes out. And so there are others, and they have their pluses and minuses, and there are companies looking at them. They are more challenging because they take a lot more energy if you like, to get to ignition, to get to that point where you're starting to get energy back again, you have to get into much higher temperatures. But that, yeah, that's not to say that they're not being looked at. Yeah, there are some of these companies on here will be looking at alternative fuel cycles. So UKAEA is mainly kind of historically had its background in jet, which is magnetic confinement fusion. That's where almost all of its expertise really lies. So it's kind of going down that Spherical Tokamak route.
That's true.
Well, so jet is an experimental reactor, so they run different campaigns. So it is a machine that is capable of running tritium, and it has done recently. The kind of big news articles that were around a year or two ago, when they talked about pulse length and energy that they managed to sustain. That was a tritium campaign. So they do run tritium on jet, but they don't do it all of the time because it's hard to do. You contaminate the machine, and if you don't need to use tritium, then you don't use it. But when you really want the highest performance, then you have to use tritium. I mean, it's like I say, it's the biggest machine capable of doing tritium in that way. So yeah, you're right. It does do DT fusion, but it also does DT fusion as well.
Like everyone's saying, thinking of the extra energy needed so much.
Yeah. And so some people will agree with you and say, yeah, I think that we should avoid the 15 problem and use a different fuel cycle. Because yeah, some people, and time will tell. We'll see. We'll be able to look back in the future and know which ones turned out to be best. But none of them give you anything for free, unfortunately. So when you get rid of one challenge, you do create one.
Just a question on the sort of timeline. Do you think it's sufficiently long enough to establish a UK origin? And then once that, does it have to be perfect for step or the companies to actually very much and origin actually not and actually the top to use the farm and optimize?
Yeah. No, I think the way I think about it, I'll give my personal, which I'm sure is not necessary. I don't know what the kind of UKAEA answer is on, but my personal answer would be that you have to see STEP in context. So STEP is one power plant development project amongst several in the UK alone. So there are others like Fusion, which I mentioned, like Tokamak Energy, which is spin out of Cullen originally. So it's also looking at technology. So they will all have slightly different requirements and designs and needs. And I think that the capability that STEP creates should serve those customers as well. So it's not about creating specific supply chains for STEP. And then on that sort of timescale question, I mean, that is a tricky one because UKAEA gets pulled in both directions at different times. Like you're saying, is that enough time for us to really get the technology right and make sure we get the right technology in place and the right capability in place? Should we, won't it take longer, don't you think? Or then others will say, why aren't we being more ambitious? Why are we waiting until 2040s to get over too late by then? So, I think STEP is incredibly ambitious. It's looking to leap effectively from a highly experimental spherical Tokamak machine in Mars straight to a power generation machine. Most private sector companies are looking at doing an intermediate machine, which isn't necessarily fully fuel sustainable or fully power, delivering commercial levels of power. So I would say that, STEP is ambitious enough as it is. I don't think it can really go much faster. I think that but it will, by doing that whole power plant design bit, it will force the industry, whether that's in the UK or whether we end up getting some international suppliers as well, will force some of those things to be solved, otherwise we won't have a power plant.
Do we have any more questions? No, I think we can give another round of applause.
Thank you so much.
Well, no, thank you. That was really, really good.